Welcome to How Temperature Affects Atomic Spectroscopy. So, temperature affects the degree to which a sample atomizes and the fraction of a given atom in the ground state, excited state, and ionized state. So each of these effects alters the signal that we observe. So let's consider an atom with energy levels E0 and E star, separated by delta E. So we've got E0 down here and E star up there. They're separated by some energy difference delta E. Now remember that an atom or molecule can have more than one state at a particular energy. And these states are degenerate. So the number of states at that energy is called the degeneracy. So the degeneracy down here is 2, the degeneracy up there is 3. And the degeneracies of E0 and E star are G0 and G star respectively. Now the Boltzmann distribution describes the relative populations of two different states at thermal equilibrium. So it will tell us the populations of this state relative to that state. So if equilibrium exists, then the relative population N star over N naught of any two states is given here, G star over G naught times E to the minus delta E over KT, where T is the temperature in kelvins, and K there is the Boltzmann constant, which is 1.381 times 10 to the minus 23 joules per Kelvin. So also note that while thermal equilibrium does not exist in the inner blue cone of our flame here, it probably does exist in the outer flame above our blue cone. So the Boltzmann distribution states that at thermal equilibrium, and for states with the same degeneracy, the population in a more excited state is lower than the population in the less excited state, which could very well be the ground state. And note that as we move from a lower temperature to a higher temperature, the Boltzmann distribution says that the relative populations between our states should go up. That is, we get a relatively larger fraction of our molecules in the excited state compared to our less excited state when we're at hot temperatures compared to cold temperatures. So let's examine the Boltzmann distribution using an example. A sodium atom requires 3.371 times 10 to the minus 19 joules per atom in order to move from the ground state to the lowest excited state. The degeneracy of our ground state here is 1, and the degeneracy of the excited state is 2. So the fraction of sodium atoms in the excited state at 2600 Kelvin, as might be seen in an acetylene air flame, is then given here. So we plug in our values. We've got our degeneracies of our states there. We've got the energy difference. We've got the Boltzmann constant here, and we've got our temperature, and that gives us a value of 1.67 times 10 to the minus 4. And note that this is under 0.02%. That is, most of our atoms are still in the ground state. There are just a very small number in that first excited state. But if we raise the temperature just 10 Kelvin, then we've increased the temperature to 2610 Kelvin, and now our value goes to 1.74 times 10 to the minus 4. And the fraction of atoms in the excited state is still less than 0.02%, but it's increased by 4%. And this means that increasing the temperature of the flame, even a small amount, just 10 degrees, can have a significant impact on the excited state population. So changing that flame temperature by 10 degrees Kelvin can alter our signal seen by 4%. At 2600 K, then over 99.98% of sodium atoms are in the ground state. And raising the temperature by 10 K will not alter the population of the ground state significantly, which means that a 10 K difference will not significantly alter the absorption signal that we see, because absorption is occurring from the ground state to the excited state. We're not significantly changing the population of our ground state, so we won't significantly change the absorption. But the emission is arising from the excited state atoms, not from our ground state atoms. Which means that the excited state population is increasing by 4% with a 10 K increase in temperature, and that means that the emission intensity will therefore increase by 4% when the temperature is increased by 10 K, at least at 2600. And this means that the atomic emission requires a very stable flame. And this is why atomic emission almost always uses inductively coupled plasma for atomization, because the plasma temperature is much more stable than the flame temperature is. So table 20.3 in the book shows that the populations in the excited state at 6000 Kelvin are 2 to 5 orders of magnitude higher than at 2500 Kelvin. Note that this is 2 to 5 orders of magnitude, not 2 to 5 times larger. And that was how temperature affects atomic spectroscopy.